Okay, maybe that's better.
Okay. So let's begin with the first lecture by Professor Shaffer. Very fascinating emerging area of Rydberg-based sensing. Please.
Thanks, Hossein, and thanks for having me talk today. So this is a new lecture that I haven't given yet, so you're kind of the guinea pigs for the talk. But what I'm going to try to do in this lecture is give you an overview of Rydberg atom-based sensing, and Rydberg atom-based sensing is really sensing radio frequency electromagnetic field. I'll tell you why this is important and why we're doing it. But I will take a step back a little bit and try to talk about, maybe touching back on what Tillman said in the first lecture about quantum technologies. I'll tell you about my institution a little bit, what the aims of the institution are, the goals, and also that will give you kind of context for the research choices along the way of my 3 lectures. I can't tell you everything about Rydberg atom-based sensing, but I think I can give you a pretty good flavor of it. So I'll also talk a little bit about the basic physics elements with regards to quantum optics in this talk. I'll cover some things about vapor cells and more kind of, I guess, contemporary things that we're working on tomorrow, and then sorry, it's on Wednesday, and then on Thursday I'll talk about sensing time-dependent fields. So I'll kind of cover an overview of a lot of the interesting areas in this field. But I do want to take that step back and say how the thought process of doing what I would call applications-based research is different than basic research, and I like to kind of link them together. I will, I think, be able to link both the prior talks to my talk here in this very applied. I guess I'd say it's very applied. Yeah. So, Quantum Valley Ideas Laboratory is a not-for-profit research institute that's a charity, and the mission statement here really is to really take things that have been done in the laboratories over a long period of time and try to commercialize them in the end, try to advance that technology to a point where a company can take it. And this is kind of the goal of all quantum technologies, but it's what happened to my slide there? It just vanished. That's the goal of most of the idea of quantum technology, but it's not an easy thing to do. These systems are still very complicated. And it takes, at least in our mind, it takes a team of scientists and engineers, but also a business team. And it's a hard kind of group to get to all work coherently together. This is a simplified kind of idea of what I'm trying to talk about. We all know that this is kind of simplified because these 2 boxes, or these 2 circles, sorry, overlap quite a bit. But and if you would go to my laboratory, which there's pictures of different pieces of that laboratory here, you would think it looks just like an academic research laboratory. Where I think the difference comes in is that instead of doing curiosity-driven research, which is really research based on trying to expand knowledge, we're doing application-driven research. And so what that means is that some of the problems that people here might think are dirty problems that you would bypass and not be interested in, we actually have to solve because we're trying to get specifically to some end goal. That's an over-trivialization, but that's the real difference between what we're doing and what you might do in a lab at a university. Now, there's another piece of this, which is commercialization, which is also non-trivial in order to, get these technologies out into the real world so people can use them, is really the goal of industry, which is productization. And this part is pretty complicated. complicated as well to take something that's in this regime and actually productize it is also non-trivial, and it's very hard to talk with these people. So you have to make a lot of effort to do that because these people don't care if your thing is quantum. They don't care at all. They want it to be somehow better than what they have by a significant factor too. Okay, so it can't just be like 2 times better, because if it's only 2 times better, they have to change everything they're doing already that works and use your thing. So these people are always asking, well, how is it 10 times better? And what I hope to show you in the talk is that better doesn't always mean that it's more sensitive. What it means is that it can do new things, or that it might be smaller or cheaper to make. Okay, so in my talk, you'll probably see references to kind of trying to move this towards that, and that's one of the things I hope you get out of these lectures. There's a lot of interesting physics and engineering in this regime, and there's new things that come up all the time when you're working here. And I'll also talk about some of the cool things there, and those are things you might want to focus on just out of pure interest. But I also want you to keep in mind that there's a reason why we're spending a lot of time on some of the things we're spending that time on, and it's to get really over here. So in Waterloo, where I work, there's elements of all these pieces in what we call the quantum valley. That's where the name comes from. This is just to not sell you on this. This is to show you one approach to trying to push all these things together and coordinate them, which is, as I said, difficult. So there's Quantum Valley Investments, which is a venture capital firm because companies need money to do stuff. There's research labs here that are Quantum Valley Ideas Lab, which are more applied. Then there's also academic research labs, which we interact with at the University of Waterloo. And then there's a theoretical institute in Waterloo called the Perimeter Institute, which is just doing theory, some of it very far away from what we're doing. But the environment here means people, and the shared environment means that people talk about the physics. In addition, one thing that is not appreciated is that there's also a business school element to this. So there's a business school program here that trains people to be executives in advanced technologies, which is very important. The reason why that's important is that they need to be able to talk to these people in order to do anything, to drive. I don't know why this is. There we go. These guys have to be able to talk to these guys, and also there's other kind of issues in all this do things like that, take strategies. Okay, so what do I mean by advancing a quantum technology? One of the great examples of a quantum technology that is commercialized is the chip-scale atomic clock, which probably all of you have heard about. Really, atomic clocks. This is really annoying, but I'm not hitting any buttons. You just. Yeah, maybe. Yeah, that might be it. This is not. Let's see if I can relieve. No, it's already got a stress relief on there, so it's already that. Okay. So one of the examples of quantum technology, as I said, is a chip-scale atomic clock, and that was a long process to get from here to here. Now, again, I'm kind of making this cartoon to make a point, is that it's very hard to take something that's a tabletop type of experiment, which is what this cesium beam clock was in 1955, to something that's small and compact and can be used in the field. Now, there's a lot of different clocks along this path that are useful, but again, part of the job of taking something into a market is to actually make it so that it's useful to a broader number of people. And the point I want to make, which you should connect with the talk, is that this clock doesn't even work the same way as that clock works. There's a lot of different things that had to happen and advances that had to be made to make this thing function. So this has lasers in it, right? This has a vapor cell in it, and it has a lot of semiconductors that didn't really exist there. And so this is a long process, and you have to work on all those things. But we're hoping to do this faster, you know, in the modern times by trying to find these things and work directly towards them. Okay, so why Rydberg atoms? Well, kind of all know what Rydberg atoms are. They're atoms that are in a highly excited state. I think a broad interpretation of that is that N has to be larger than the valence state. And these atoms have many exotic properties. And we've studied them for a long time, for over a century. So Chris gave you a nice talk about quantum defect theory, which shows there's a tool that shows that we understand these atoms very well. Okay, so the fact that we've studied them for a long time means that we have lots of tools to interpret it and interpret, you know, how these atoms interact with light and how they're structured. We understand their structure very well. So Rydberg atoms also played a role in kind of fundamental physics at the very beginning. But like I said, I think they're transforming into tools for quantum technologies. Why is that? Well, that's because we can, with light, excite many of these different states with different quantum numbers, and those quantum numbers make the atom behave in different ways. And so there's these important scaling laws which tell us, you know, how different properties of these Rydberg atoms scale with principal quantum number, namely, but we also can understand how they scale with angular momentum quantum numbers as well. And so these atoms are really like tunable quantum systems. And that's important because despite, you know, many, many years of work in fabrication, it's still hard to make artificial quantum systems with enough robustness and uniformity to use in many of these quantum technologies. So what the Rydberg atom offers us, and I think you can see in the work on quantum simulators, the work on quantum computation, and the work on RF field sensing, is actually a tunable quantum element that can be used for technology. I hope I'll show you that. Okay, so what are we trying to do with this, these atoms? Well, what we're trying to do is kind of replace antennas. And if we're just thinking about test and measurement, what we're really trying to replace are calibrated dipole antennas. So you all know basically how this antenna works. There's electrons in here, they slosh around when the field hits them. That induces a voltage across the two elements of the antenna, and that's what's read out. There's an electrical readout. What we want to do is replace that with a different system that is just based on light and atoms contained in a dielectric container. So here we have two laser beams that come through, and they prepare and also read out the atoms inside of the dielectric container. Okay, so this is all coupled through light, so it can also be coupled through waveguides like fiber, things like that, and it's read out by light. And then also this part here is important because it's dielectric. So this is metal, and if you take this, especially at high frequencies, and stick it next to the device you want to measure, you won't just measure what the device is producing, you'll measure what the coupled device plus antenna measures. And that's less true here. And a lot of the physics I'll tell you about, probably not today, but tomorrow, is about making it so that this thing is even less perturbative it would be if it was just in a glass vapor cell. The other thing that's nice is each of the atoms is acting as a little sensor of the electromagnetic field. So this means that you have spatial resolution that's sub-wavelength in these devices because you're not fixed to some length to extract the measurement of the field. Okay. All right. What are other important things? Well, because you have to make the antenna a certain size to sense the field, there's a limitation, just a physical limitation of how big those antennas can be, and that's about here. Rydberg atoms have a spectral bandwidth. This would be for the carrier bandwidth it would sense. It's very broad. You know, it can be up to 300 gigahertz, maybe a little more, but this is kind of the measure that I kind of use. And there's a lot of applications in this area for sensing RF fields. That's why this technology is important, and there's no other alternative technology really to antennas. And there's a problem at higher frequencies here, and there's even problems with calibration and things in this region, okay, of the spectrum. This region of the spectrum here is called FR2 bands. This is where you have your 5G Internet of Things and stuff like that. And there's a pressure to move devices up this scale into higher and higher frequencies. And that pressure is because we use the electromagnetic spectrum for so many things like your cell phone communications, radar, all kinds of different signals, that this spectrum becomes very valuable. So there's international organizations that chop out different spectra here for use in different industries and by different people. And people in other fields can't invade your spectrum. So people pay billions of dollars to chop out a little niche of the spectrum. Okay. So if you want to make new things, you might have to move up here. Now, of course, every one of these frequencies is not good for all applications. So, examples are down here is more for communications because there's more transmissibility through the atmosphere. And, yeah.
This thing known as this sort of terahertz gap, which is in fact reduction of astrophysical molecules, rotational spectrum in the higher.
Yeah, so I think that's like kind of like in here, because I think you need higher is terahertz, and that's because also you need bolometers, and it's not very good at detecting. We have some ideas to take this to higher frequencies, but not the same modality. Yeah.
They have to use all the sort of the shelf stuff, the old telescopes, things to make their
Yeah, it could be. I mean, that's one of the things is to open up this spectral range, whether it's just for testing and there's other devices there, or whether it's as a detector itself. It's hard for me to talk about all the applications for this, and I've chosen a subgroup. And one of the things that probably you should get out of this in the end, as I go through these things, you'll see that I'm gonna, for different applications, the ones I've chosen, I'll grab different pieces of this system and put them together and optimize them. So maybe you're a little bit familiar with this field. You're thinking about a tabletop experiment with lasers passing through a glass vapor cell. So one of the things that's important to tailor this to a particular application really is to take and change the vapor cell around and make sure that it's the best suited for that particular application. Because if you're trying to make something that's a jack of all trades device, that's not a very good strategy, because you can compromise on other pieces of the technology if you really are shooting for one particular thing that you're trying to do. So it's important to know what you're trying to do, and that kind of ties back with my little soliloquy about application-driven research. That you kind of want to know what you're trying to do, where you're trying to shoot for, because that allows you to kind of cut things out and focus on other things. You know, the two main areas that we've been working on are this test and measurement aspect of these sensors, but also for radio frequency receiver, or mostly for radar. Two things I'll talk to you about. So this is one of my favorite slides. I use it in all my talks. It tells you exactly how this works. So you all know that if we scan a probe laser across a resonant transition, and this is kind of shown for cesium, that we would get an absorption dip here. I didn't include any Doppler broadening or anything here to make it simpler. If we add a second laser that we usually call a coupling laser, then what we can do is we can induce a narrow band of transmission within that absorptive feature. And I'm going to give you the first interpretation here of why that happens. And later on, I'll give you the alternate interpretation of that. But I think both are good to keep in mind, and I'm going to try to emphasize these, kind of simple explanations for things. So what we can do here to first order is get an interference between the processes of just absorption on this transition, and then absorption of one of these photons, and then a Rabi flop up here. Okay, those two processes are out of phase. Now there's other higher order processes that happen too, but let's just stick to the lower order process. So those two things are going to interfere with each other, and we can get a high visibility of that interference. Basically, they can cancel if we can make this strong enough so that the second process can be the first, or they're the same. Okay, so that's because those amplitudes in quantum mechanics add, and so if they're equal and opposite sign, then we're going to get 0, and we'll get the cancellation of absorption on the resonance, and so that's your electromagnetic diffuse transparency. So this gives a narrow feature that's can be sub the line width of what you would get on this transition. So that's important for this method because, as I'll show you here, how the sensing takes place. The other thing is we want to do this in a vapor, a hot vapor. You don't want to have to use laser-cooled atoms and put metal vacuum chambers around it and such, and a bunch of other lasers and optics. So we need a technique that is a sub-Doppler technique. And this is pretty good sub-Doppler. The K vectors of these two lasers reduce the effective line width of this feature. Okay? So how does the sensing take place? This is kind of the readout and preparation. And maybe I'll take a break here before I really go on to that part and say this is related in Rydberg physics to one of the things Chris Green was talking about at the end of this talk. So we can kind of think about this as sculpting the Rydberg atom to do a particular task. So what we're going to do is make this particularly sensitive to what happens up here in this level by doing this. Chris was talking about how in order to induce these AC Stark shifts in I think it's a quantum simulator, that it was better to use this auto resonance where there was a dip in the ionization probability. And so that was taking lasers and changing the atom around a little bit so that it can do the task you want. And that's the other benefit of knowing the system so well that you can actually engineer it. You can engineer it with laser fields. It's the control that's kind of offering up a lot of these new opportunities, the control over the atom. All right, so let me just keep going here. So now, if this is a Rydberg state, we can take a microwave field that's resonant with another Rydberg state, and if that's applied to the system, it kind of breaks the symmetry, and what it can do is it can split this state, and we can resolve that splitting of the EIT resonance. And this is, to the simplest way of thinking about it, just an Elder-Town splitting of those two transition speeds. So it's reflective of the power in that microwave field. And the splitting here is given by that Doppler-Towns, or the Rabi frequency, the Doppler-Towns splitting between the two peaks, which is just the magnitude of this electric field dotted into the dipole moment of the atom divided by h bar. And one of the important pieces of this technology is that it's what's called self-calibrated. And what that means is that you don't ever have to take the antenna to and calibrate it against something else, because you're calibrating it to the atom. Because this electric field is directly proportional to how you would measure this, which is a frequency measurement. So it's insensitive to how much gas and things are in the vapor cell, or the temperature of the vapor cell, for example, the laser intensities. And the structure of the atom, which is this part of things, the dipole, the transition dipole moments. This is an exact number now, right? So that's what this is meant to be self-calibrated. So frequency measurement and calibrated to the atomic structure itself. So you can go to a precision laboratory and try to measure this more and more precisely to get a more and more accurate value for this electromagnetic.
Maybe just explain why the peaks, like the other town peaks. Oh, that's true.
Yeah, this is transmission. Yeah.
Oh, okay. Sorry.
Yeah. Yeah. you're not the only one that gets confused by that. I'll try to point that out. But, and actually, Hossein and I are doing a project where we're going to try to measure these more accurately. This is actually a limitation of the method right now. It's how well those dipole moments are measured. All right. So in the end, all we're going to do is measure the transmission of a laser through this atomic sample that's contained in the dielectric container. And really the technology is pretty much that simple. We're going to measure this as a function of frequency, or we could measure it as the amount of transmission, but that's a measurement that's not particularly self-calibrated. Okay, so we're really just kind of making the atoms in this vapor cell sensitive to that RF field. So we're using light again to maybe tailor the atomic response to an incoming RF field. Okay, that's really that simple. This is some old data on that for rubidium. You can see the line splitting here in response to an RF field that's applied. This is the peak splitting versus the electric field, and it's linear as you expect. In this case, what we're doing is we're scanning the probe laser. In that case, there's a little bit of an extra factor here due to Doppler effects in the vapor cell, and I kind of retained this to mention that the Doppler effect in the cell is actually important, and you have to think about that. You can change some of the results and expectations, especially in this other regime we call the amplitude regime, just looking at the change EIT peak height. If we scan the coupling laser, this thing goes away, which is what we usually do, because we do want this thing to go away. We can measure the splitting and the splittings here to around 0.5%. I don't know, maybe a little bit better now. It's kind of an old slide, but still, the dipole moment uncertainty is still around 1%. And that's kind of the limitation of this technology is. But this is actually a very, very good number for RF technology, because at these higher frequencies, and by higher frequencies, I mean really above 20 gigahertz, the power measurements from these calibrated antennas are only good to about 4 to 20%. So it's already better than that. And also it being, a bit better and even, pretty much the same at very low frequencies. I'll point out that when you're doing calibrations and testing, it's good to have an alternative method to measure something, right? And this is a completely different measure of those fields than an antenna is. So now you're comparing two different, radically different ways to measure that electromagnetic field. Also point out here, going back to the scaling laws, that the reason why this is sensitive is because of those n scaling laws for the transition dipole moment. So, you know, there's a neighboring, for the transitions between neighboring states that scales like n squared, and you really get, you know, really large transition dipole moments. So we're taking account, or we're actually taking advantage of resonance. So in sensing, you always want to kind of take advantage of resonance because it's hard to be, you know, resonant. And that's the property here that we care most about. I will point out that later in the talk, I think it's the third day, I'll talk a little bit about collisions, but it's the same thing that leads to large cross sections for collisions between Rydberg atoms, right? So that's actually a disadvantage for us there, is that we have to kind of keep these samples dilute enough that we don't have the measurements disturbed by collisions. All right. So this is maybe a summary of the advantages, some of the things we might want to mix in together for a particular application. So it's self-calibrated, it's stable and reproducible. That's kind of related to the self-calibration. It's based on an atom. All the atoms are the same, so you should get the same measurement anywhere. The sensor can be made small and can sense at spatial resolutions that are sub-wavelength with imaging possible. So we've actually imaged down to lambda over 650, at least in my lab. It's optically read out, so there's no wires that are going to the device. So it's more electromagnetically transparent than an antenna. This also helps with imaging, especially in near field. Has a broad carrier bandwidth, and the polarization discrimination, which I didn't talk about, can be large. The atoms can discriminate polarization, but you can also engineer the vapor cells to be highly polarization discriminated. So maybe to go back to the physics part, the key kind of physics elements, at least in the part that I've told you about so far, are electromagnetically induced transparency, Doppler shifts, Doppler splitting, vapor cells. I won't talk about that too much more today, except maybe one thing of talking about how not to make vapor cells. Laser stabilization and control, because this device actually has lasers in it, and people get scared when devices have lasers in it. And then kind of the readout methods. So, which may be more like signal processing, which I'll talk a little bit about in the third lecture. All right. So if you don't know about Doppler splitting, this is kind of a simple picture of Doppler splitting. So if you have this laser here, and you can see by the level diagram that it's closely related to EIT. If this is strong, then you can dress these two states. And in the dress state picture, you get two levels here that are split by this Rabi frequency of this, what I've labeled here, omega C, because I stole my figure from for the next slide, which is on EIT. And those two levels, when this is strong, are mixed 50-50, but with a different sign for the two level, because it's detuned in different directions from zero, assuming that this is left on resonance here. And so this is really just a dressing picture. And again, what you get is two levels that are split by the Rabi frequency of this strong laser. So this Doppler splitting is really reflective, like I said before, of the strength of this perturber, this field. Okay. EIT is a little bit different, and it's more related to some of the things that Chris Green was talking about in the last talk, where you have interference between two levels that overlap with each other. So in fact, EIT kind of came out of the field of probably, I think it's more molecular physics, but from the same types of things like faunal resonances, and having states that are coupled into the continuum. So first kind of faunal resonance thing is you can go to the state directly, and then it can couple into the continuum, or you can go directly into the continuum. Those two processes interfere with each other. Similar thing is what I described to you in the other picture of EIT, this kind of the qualitative picture. Here, what I'm going to appeal to is the similarity between this and Adler-Towns splitting. So here the coupling laser addresses these two states and they're split. In contrast to Adler-Towns splitting, what we'd say is that EIT happens when the two states here overlap with each other, so that in between, because there's a pi phase shift as we go across this level, there's be a resonance there. And it's because there's a sign difference up here in the two level that in the dress states, as they're created by the coupling laser, that means that one of these things has effectively like a positive dipole moment, and the other one has a negative dipole moment. If you're in the middle, the two states are kind of split a little bit symmetrically about that center, then you don't know which level you're really exciting. You're kind of exciting both at the same time. Those two add, and then you get interference, especially on resonance, that cancels. Okay. When we would apply actually the RF to this, so this is kind of the first part of what I described, the kind of setting up of the atom. Well, what happens then is that these guys kind of get perturbed by the RF, and it kind of opens a window here where now there's another piece that can come up here and ruin this kind of cancellation of the EIT interference feature. Right. So now you get another kind of piece that gets a pi phase shift in here, and instead of getting now kind of perfect interference here, then you would start to decrease that kind of feature in amplitude. And that's kind of the other sensing regime that we work in, which is the amplitude regime. That's when you look at how strong this peak is. That's not self-calibrated because it depends on other factors, like the laser, like the coupling laser intensity and the absorption. The other piece that's important are Doppler shifts, because these are hot atoms. And that's the Doppler shifts in all these cases give rise to the spectral width of those different features. And you know that the resolution on how, well, basically the sensitivity that you can achieve and the resolution and electric field strength that you can obtain is going to be determined by how you can separate those peaks. And so the width matters. So, just on a rule of thumb, it might be half the half width is kind of the Rafi frequency that you can sense here. Okay, and it's pretty straightforward to do this type of averaging. You just take in the density matrix picture in steady state what effectively the dipole moment is for transition to those excited states. Adjust them so that you take into account the velocity of the atom, and then you just have to integrate this. This integration is fairly complicated, but as a kind of a rule of thumb, if we're scanning the coupling laser, these are scanning the probe laser, point out, but scanning the coupling laser, we could take the Doppler shift of the first transition, which is just that k vector for that laser times the velocity of the atom. We say that we address things that are within gamma, which is the decay constant of that first level for that first transition. And then we can look at the two-level or EIT Doppler shift, which is the difference of these if the two lasers are counter-propagating, and we insert the value for the velocity that's addressed by the first laser, because those are the atoms that are going to participate in here, and then we get a Doppler width that's around this. And for the system that I'm going to tell you about, this width is about 3.5 megahertz. Tomorrow, I guess it's a Wednesday, I'm going to tell you about a different laser scheme that more or less eliminates this width. It allows you to extend that Adler-Towns regime much farther than what it is in the cesium system that we usually use. This is just to say that in that amplitude regime where instead of looking at a splitting, we're just going to look at the depth of the T feature. That behavior actually changes. This is kind of interesting. It becomes quadratic. Here are calculations, and you can actually get a fairly simple expression for that by looking at the density matrix equations. And that simple expression converges over a longer period of time if you really are in a case where this is actually a fairly strong Rabi frequency. So you have strong EIT. This is not really important as details, but this is to show that you can understand even that other regime. So you can use it for sensing. It's just that it doesn't have this property of self-calibration, which is important to some applications. All right, so I'm going to change over to looking at some of the engineering of vapor cells, just to give you a flavor for that. And then I'll come back and kind of show you a prototype that we built where we've taken everything off the table and use it to actually do this. This should be like the analogy to be somewhere in the middle of that timeline that I gave for the atomic clock. So most of the data that I showed you so far was taken with systems that were built on an optical table. You know, in a quantum optics laboratory, you probably not think it was very different than your own laboratories. But at the end here, I'll show you something where all that stuff's been stuffed into a box, and data's been taken, you know, in an anechoic chamber. So the vapor cells are not really that easy to make because, as I'll show you on Wednesday, one of the things that's advantageous, you don't want the vapor cell to be perturbative of the measurements to make it small. So you want the sensor head, to be small. There's physics behind that, but I'll leave that till Wednesday. You also want these things to be fiber coupled, so you have to couple fiber to the vapor cell, which you can kind of see here a little bit. You also have to fill these very small vapor cells. And the filling of these vapor cells and the development of these vapor cells is very different from that you would do for magnetometry or clocks. So Rydberg atoms are very fragile, so you can't have buffer gas inside the vapor cell or background gases. So these vapor cells, you know, have to be, we had to do a lot of work to make these kind of small vapor cells so that we could get narrow line widths. And so here this shows kind of the narrow line width obtained in a MEMS vapor cell versus some large reference cell. And then a saturated absorption spectrum taken in one of these little vapor cells. So again, this is going back to my original talk, is that, you know, maybe if we don't want to commercialize this and use it for a real application, we just use any old vapor cell. But because we want to use it for, in this case, this cell is for test and measurement, because this cell actually scatters RF not very much at all. If we want to do this stuff for applications, we have to address some of those problems. You know, we have to actually engineer the vapor cells to make it optimal, because the normal vapor cells don't work. They have like lots of reflections. They're hard to make. It's not going to work for a commercialized product. This is kind of what we're working towards to make these things on. So these vapor cells we kind of quasi-make by hand. We still machine them on a wafer, and at least the center spacer, and then we put the windows on top after we fill the vapor cell. But you can kind of see on this figure up here that there's a lot of fancy machining. So these are all made with lasers and laser machining, so they can be kind of mass produced at some point. We need to mass produce them. So, you know, this is one of the things that made us choose this way to make vapor cells rather than an alternative path, because we knew that we could machine silicon well and that we could get high quality silicon wafers. So it makes sense to try to go in this direction to mass produce these little vapor cells, which are fairly complicated to make. All right, so the prototype I'm going to talk about or give you Introduction 2 has 3 different pieces. There's a little MEMS type vapor cell. So this is about 4 millimeters across here. This is maybe like 1.5 millimeters. This way, you can kind of see the green light coming through there for the, for this EIT process, which in cesium uses the 52 nanometer light beam as the probe laser, and the coupling laser is a green laser. And another thing that's here is this fiber coupling is important, and that had to be engineered too, because there's 2 different colors of light traveling down the same fiber here. And there's also assembly of this, which has to be glued together. And so even the properties of the glue in this vapor cell actually matter. Then there's an interface here, which processes the data. It basically controls all the lasers, allows you to tune between different Rydberg transitions, and has all the signal processing stuff in it. This is the box that has all the control electronics and the 2 lasers in here, and a bunch of frequency references that can allow you to tune the laser and allow you to lock the laser. You can kind of see the size of this. This is about 3 foot by 3 foot, 3 foot, something like that. So one of our next goals in the next generation is to reduce the size. That works. All right, so see, this is a little video of it working. So let me see if it's not running here. Oh wait, there it goes. So what you'll see is someone come in here and pull the antenna away from the sensor, which is right here. It's kind of a crude setup before we move this into the anechoic chamber. And you can see the peaks change in their separation as you would move the antenna away from here. If you look really closely, you can tell the person hasn't moved their hand away because they're moving around, and you can actually see some reflections of the RF, in this signal here. I think it's done now. You can also use this to measure antenna patterns. So these are basically antenna patterns of the power emitted, and these are taken at 27 gigahertz, which is not an easy frequency to measure at for these RF systems. And the sensitivity is better than maybe 0.5 millivolt per centimeter per square hertz, which is pretty good for, this is just from the Outler Towns regime, where we actually get self-calibration. This is pretty good for portable device. Here's a little bit more data, just to show that we've made experiments. This is basically the graph of applied field versus the sensed field. It should be linear. It's pretty much linear. We had to push the range in which we could tune this laser to get this overall range, but it's covering in a single measurement 40 dB of power. And the sensor still hasn't broken down up here. I'm sure that this goes up quite a bit higher until these states start to collide with the neighboring Rydberg manifolds that you saw in some of the other talks. I think I'm going to try to finish up here soon, but we also can make interesting measurements that are kind of new compared to other devices. So this is actually an out-of-band interference measurement. And in a normal measurement, when you have a power meter and you take a bandwidth in there, you'll get all the power that's in that bandwidth. But in this sensor, you can actually look at a wider bandwidth, and you can deconvolve the 2 signals from each other because you get 2 different slittings for the 2 different powers. So you can actually see multiple independent signals coming in at the same time, as long as they're at different frequencies. They're at the same frequency since the electric field's at, and you're not going to get a different measurement. But if you have an out-of-band interferer that's displaced from the sensing frequency by some amount, you're able to sense both at the same time. So what this is the power that's sent on the target as a function of how far the out-of-band interferer is away from the target. And you see that you don't get a jump in the power until you get within the sensing bandwidth of the two devices when the two signals start to overlap. Normally, this would be around 15 millivolts per centimeter, but it's only at 10 because the phase of the perturber is different from the phase of the target here. These would add up when they were together if the phases of the two frequencies were the same, but they're not in that case. Anyways. So I'd like to kind of conclude here, and then I'll show you what's going to happen in the next two lectures. I think, especially in quantum technologies, it's important to think about your research objectives, because I think that could tailor the work. So especially in my work, that's what I have to think about all the time, is what are we trying to get to, and what can I cut away, what do I have to optimize? You know, in basic research, you do a little bit of that, but I think since I've done a lot of also basic curiosity driven research, I know that what I do now, I have to think about things in quite a different way. Also, hope you gave you an introduction to Rydberg atom-based sensors and showing you that they're a fundamentally new way to detect and measure radio frequency fields. There's a lot of unique qualities of this sensor, and it's promising for test and measurement, also promising as a receiver. And it's important to realize, if you're ever going to work in this field, that it's a different way to sense electromagnetic fields. It's not the same as an antenna. So you have to think about, and this will be on day 3, I'll show you an example of that, where we thought of the sensor in a different way. We thought about it as a Rydberg sensor, not as an antenna. So we had to change some things around in signal processing to adapt to that. There's a lot of interesting physics here. You'll get a flavor for that in the next 2 lectures, maybe especially on Wednesday. And things like engineering the sensor head, for example, are important to optimize its method. So this is the lineup for the next 2 lectures. So next lecture, I will tell you about some new technologies, new spectroscopy, and I'll tell you a lot about vapor cells and how to understand them. Some new kinds of vapor cells, photonic crystal vapor cells. And then on the last lecture, I'm going to tell you about time-dependent signals. And this is kind of where, like I said, just to maybe spoil the lecture, we have to look at the response of Rydberg atoms, not of an antenna, in order to optimize the reception of pulses. You can't think about this as an antenna and then expect to just plug it into the back end of something that would do signal processing for a conventional antenna. So anyways, with that, I'll end, and hopefully you have some questions. Yeah. It's a quasi-continuous spectrum, but you can tune roughly plus minus 200 megahertz around each of these transitions, so there's almost continuous coverage. It's when you get to the very high frequencies, that's where it starts to get a little bit more spotty. There might be some hole.
Are there effects from stray fields?
There are effects from stray fields, so part of engineering those vapor cells is to reduce that effect in the vapor cell. That's an important issue. So that's one of the main broadening mechanisms of the spectral line in a small vapor cell, and that is something we spent a lot of time with. That it's again another example of something that people might think as dirty physics, but it's important physics for this application.
Can you actually also do like direct phase sensing or direct polarization sensing that?
We know how to do direct polarization sensing. We know how to do direct phase sensing. I'm not going to talk about that here. When we talk about phase, things get a little bit more complicated, because there's a question about well, what kind of phase do you need? Do you need a phase reference to something, or do you just need a relative phase across all the time?
Well, what happens if the microwave drive is very broadband? You can still extract spectrum.
You can, but that's not kind of where it has its strength. You know, you'll get a really like, I mean, if it was separated by too much, you probably wouldn't see the components that were at frequencies that were out of bandwidth for the sensor. In band, you would see kind of a mush of stuff, and you probably can still get some information, but that's more complicated around designing that. I would say that you probably get the mush of stuff in a conventional antenna as well. So most applications like communications, radar, and contested measurement, you've already selected your carrier frequency and your baseband. You know, your baseband might be something, but you know, a channel baseband even in communications is not that wrong.
Is there a particular reason why you choose CDM instead of PDM? Because PDM has like two legs that are closer in terms of the data.
Well, cesium actually has better matching in this 3-photon scheme that I'll tell you about on Wednesday. But that's not the main reason we chose cesium. We chose cesium because it has a single isotope.
This might have been on the slides, but how strong do you find the microwave field has to be for your dominant sensitive?
So in the kind of outer toms regime, it's probably like around, in the prototypes, the best one, because that's the real thing, you know, 100 microvolts per centimeter per square root hertz is probably where I'm in the outer toms regime. And, you know, without doing kind of anything more in this amplitude regime, you can kind of get down 7 microvolt per centimeter square hertz. There's other people who have used auxiliary fields and heterodyning technique to even get higher sensitivity. But then you lose a lot of stuff. You're not self-calibrated, and you're also limited by the antenna that you have to use to do the heterodyning. So it's okay for some applications, but not all, particularly not a lot of the applications we're talking about here. We have done work on doing heterodyning. We have some patents on that for doing like holography and things like that to extract things. So that's one way you can extract it in a controlled environment where you have control over that field, that reference field.
From the radar side, I see the content. From the industry side, is there some barriers that you think people would like the updates or slow?
I think it's like understanding the technology. So we spend a lot of time talking to them, and then also, you know, partially working with them. I think they're like, maybe this is like this is kind of maybe there's a broader answer to that, in that one, they don't kind of care about how it's made, they just want it to work. So that's the easiest way, is to get just insert the thing into their product line. But with quantum technologies, that's probably not going to happen because they're different. So you have to educate the people a little bit. So for example, our prototype is a good prototype to show and demo to them. But you know, the next generation is supposed to be more like turnkey, where you don't have to be a PhD to operate it. You don't have to do that here, but you know, it's not 100% robust. You know, I mean, I have picked it up and dropped it, and it still works. But you know, when some people come by and can you drop this out of a helicopter? No, it's not gonna happen.
Can you actually even put a camera on that for I mean, now the record of those microcells or microwave cells and raise microwave cells?
Well, I'm sorry, I didn't catch the whole question.
Like, can you put like a camera for gigahertz or terahertz radiation with such an approach?
Yes, you can. So it might not be the best to use those tiny vapor cells like I showed, but we have developed vapor cells that are plate-like vapor cells, which are engineered so that you don't get reflections off the side of the vapor cell. So they don't allow much propagation in the transverse dimension when the RF field is.
Take a measure and not because of this, because it means this is possible.
So you can, can you measure frequency modulated signals? Certainly with the heterodyne you can, but there are some limitations to the speed. So maybe one disadvantage to this is that the baseband might be not as broad as what you could do in a conventional antenna with conventional electronics. But it's still around 10 megahertz or so. Easily, you could probably stretch it to be more than that. So you can detect frequency, you can detect phase. Those two things are harder, and some of the methods to do that involve compromises on other aspects of the sensor. So there are reasons to do it, and you can do it.
Just one question, I'm not sure whether you're allowed to talk about it, but what will be the first application of this? I mean, what is the
So I think
first customer?
well, I can't say that we are spinning off. So that's another whole. We are going to spin off a company, and it's going to be a single sensor with a reduced version of the prototype that I showed for basically a alternative spectrum analyzer with some of these these other qualities. That would be.
Spectrum analyzer.
It's basically a power analyzer that is, that senses only in a particular frequency band. So that's the.
Who buys that?
So that part I can't talk about, but I could generally talk about would be most of the test and measurement companies. So you can guess who that is. I mean, yeah. So they're all interested in this technology. They all have some small investigations. We have arrangements to go see them and show the data and stuff like this. But they're interested in it because there's really I can't emphasize enough that if you want to do quantum technologies and you're really seriously thinking about quantum technologies, you really have to think about what the application is and what the problem is. The problem is the most important piece. And the problem that this solves is that with very complicated antennas that are used for 5G at high frequency, you can't do conductive measurements anymore. If you detach a cable and you attach another cable, first of all, you won't get the same result. Second of all, those devices usually couple to the antennas. And third of all, those devices become quite complicated because they're multi-element devices. So you have to do over-the-air testing. So all these test and measurement companies, all these communications companies are worried about over-the-air testing. And this is a solution for over-the-air testing that's self-calibrated. So we're also working with the NRC in Canada, the project that Hossein is part of, to try to push this towards being a primary standard. So if that was the case, then it would allow companies to take their so-called kilogram into the lab themselves and make these measurements. So quantification of this, because of the standards as well, is important. So there's kind of a lot of pieces in there. But the bigger, other piece that I was throw out there is that, an established tier 1 company wants to slot in a product. They don't want to have to figure it all out themselves. So usually these things start off in spin out companies, get developed, and then the bigger companies will eat them up and buy them. That's kind of a typical process.
Yes, FM radio is not one of them.
Probably not.
Oh, perhaps maybe I'll ask a question. I think for these vapor cells, so the stray fields are important because you need to reduce volume effects. How about the surface field fluctuations? Are they going to be?
They are. We're not. We kind of try to keep the. I'm going to talk about vapor cells tomorrow, but keeping the sensing region kind of away from the surfaces is somewhat important. So they're not really just above the surface. They're usually far enough away that kind of thing doesn't matter, but certainly charges, stick to the surfaces are, so sometimes we'll fill vapor cells with getters because it's easier, it's an easier process than filling with pure metal. And in the getter activation, you usually generate a lot of ions because you're basically generating a plasma. And so we have to take some special measures to try to get reasonable line widths and do something like that. But it's an easier way to prototype.
Thank you. Plenty of questions. I'm sure there will be more. There's time for that also, lunch, and then in the afternoon. But join me, thank you, Professor Shaffer. And all.
Thank you.
Lunch is served already, and then you have some free time. Okay, it's nice outside as well. But then you can use perhaps the free time to
Oh, sorry. Forgot about that part.